Hi there. Glad to have you back at Dr. S's Random Math Lair. Today's video will cover a mathematical technique used in constraint optimization, which involves minimizing or maximizing a function given a set of constraints that are to be satisfied, in the form of problem 3. We refer to this particular technique as the Lagrange multiplier method, and it is often studied in multivariable calculus or vector calculus at the undergraduate senior level, and first-year graduate level. Here's the statement of problem 3. Use the Lagrange multiplier method to find the absolute maximum and absolute minimum of the function f of xy equal to 6x squared minus 3y, subject to the constraint g of xy equal to x squared plus y squared equals 2. Here are a few important quick facts and review that we will need to solve problem 3. First, let's consider smooth differentiable real-valued functions f and g in n variables, where we write them as f of x1 up to xn, and g of x1 up to xn, respectively. For all intents and purposes, we shall assume that n is greater than 1. Now let k be a scalar constant. Consider the gradient of g of x1 up to xn to be a non-zero vector for all points x1 up to xn, such that g of x1 up to xn equals k. The Lagrange multiplier method allows us to maximize or minimize the function f given the constraint g, equal to the constant k, by solving, for all points x1 up to xn, the equation given by the gradient of f equal to lambda times the gradient of g, for some constant lambda. We label this as 1. This constant is called the Lagrange multiplier. Note that it is possible to have a function subject to more than one constraint, and hence, more than one Lagrange multiplier. With that, one must be careful not to exceed the number of variables in the system. Since this generalization is beyond the scope of this video, we shall only stick to the case of a function subject to one constraint, with one Lagrange multiplier here. Let's solve problem 3. But before we do that, note that the constraint g of xy is the equation of the circle centered at the origin with radius the square root of 2. So for the constraint, the largest possible range for x is between the negative square root of 2 and the square root of 2, and the same goes for the largest possible range for y. Therefore, by the extreme value theorem, we know that there are absolute extrema occurring within these bounded ranges for x and y. Using partial derivatives, the gradient of f of xy is given by 12xi, minus 3j, and the gradient of g of xy is given by 2xi, plus 2yj. With lambda denoting the Lagrange multiplier, we have the system of equations star, given by 12x equals 2 lambda x, negative 3 equals 2 lambda y, and x squared plus y squared equals 2. Note that we cannot have y equal to 0, lambda equal to 0, or both, since that would violate the second equation in star. From the first equation in star, either x equals 0 or lambda equals 6. We are not finished with this problem yet, for we still have to determine the possible absolute extrema of f. Let's do that next. We continue to solve problem 3. From where we left off, for the case where x equals 0, by the constraint it follows that y equals plus or minus the square root of 2. So this gives us potential absolute extrema of f at the points 0 plus or minus the square root of 2. For the case where lambda equals 6, from the second equation in the system star, y equals negative 1/4. So from the constraint, it then follows that x equals plus or minus the square root of 31 all over 4. Therefore, f also has potential absolute extrema at the points plus or minus the square root of 31 all over 4, negative 1/4. Evaluating f at these points, we find that f of 0 plus or minus the square root of 2 equals minus or plus 3 times the square root of 2. Also, f of plus or minus the square root of 31 all over 4, negative 1/4, equals 99/8. Consequently, f has an absolute maximum of 99/8, at the points plus or minus the square root of 31 all over 4, -1/4, and an absolute minimum of -3 times the square root of 2 at the point 0 square root of 2. Observe the sketch in figure 1. The blue circle is the constraint g of xy, while the dotted black and solid red curves are the function f of xy equal to various values of the real constant c. In particular, the top solid red curve corresponds to c equal to the absolute minimum of f, and it touches the graph of the constraint at the point 0 square root of 2. So the two graphs are tangent at this point, implying that their normal vectors are parallel, that is, the two normal vectors are scalar multiples of each other. In mathematical terms, this means the gradient of f is a scalar multiple of the gradient of g, and that scalar multiple is precisely the Lagrange multiplier lambda. Note that if c is smaller than the minimum value of f, the graph of f of xy equal to c does not intersect the graph of the constraint, so f does not satisfy the constraint. Likewise, if c is bigger than the minimum value of f, the graph of f of xy equal to c will intersect the graph of the constraint, but the two graphs will not be tangent at the intersection points. Finally, the bottom solid red curve corresponds to c equal to the absolute maximum of f, which in this case occurs at 2 points. One can make similar observations as we did for the absolute minimum of f.